Okay, sir. Good afternoon to present here. Welcome to the fifth day of ILLUMINISMO 2021 webinar series on emerging trends in interdisciplinary sciences and social sciences. Today, the Department of Physics is organizing the webinar on the topic Raman Spectroscopy and the detection of chirality with the eminent resource person, Dr. Debraj Gangopadhyay, postdoctoral researcher at Institute of Organic Chemistry, Czech Republic. Welcome you all to this webinar. Now, I would like to invite Dr. Shitu Abraham, Faculty of Department of Physics, to welcome the gathering to listen him to lead the webinar. Over to you, sir.
Okay, thank you, Adona. Very good afternoon to all. Dear Dr. Debraj Gangopadhyay, our renowned invited speaker of today's second session, our principal and organizing committee chairman, Sri Biju Joseph sir, organizing committee convener, Dr. Sinod Karyachan sir, also other members of the organizing committee and technical committee members, faculties from our institution as well as from other institutes, research scholars, and my dear students. As we entered into the fifth day of our international webinar series on the emerging trends in interdisciplinary sciences and social sciences, ILLUMINISMO 2021, I'm extremely happy to introduce and welcome my friend Dr. Debraj Gangopadhyay in front of you for the technical session of Physics Department of St. Vincent College, Rajapuram. So, we the St. Vincent family wholeheartedly welcoming you, dear Dr. Gangopadhyay, for this program.
Thank you.
I am extremely happy to welcome our principal, Sri Biju Joseph sir, the chairman of the organizing committee, Dr. Sinod Karyachan sir, convener of this webinar series, Dr. Ajit Kumar K, the head of Physics Department, Ms. Parvati E, and Dr. Monisha PJ, the faculties of Physics Department, and the other faculties from various departments, as well as other research scholars, and my dear students, to this scientific session. Before going into this session, let me say a few words about our speaker, Dr. Gangopadhyay. Dr. Debraj Gangopadhyay, or in other name Debraj Ganguly, is currently working as a postdoctoral scientist in the biomolecular spectroscopy group of Professor Peter Bohr, Institute of Organic Chemistry and Biochemistry in Prague, Czech Republic. He completed his schooling and bachelor's studies from his hometown, Kuch Bihar, in West Bengal, and did MSc in physics from Banaras Hindu University, Varanasi, in 2010. He obtained his PhD in 2017 from the Raman Spectroscopy Laboratory of Professor Ranjan Kumar Singh at Banaras Hindu University, Varanasi. Then, during his PhD tenure, he also worked as a research scientist at the Raman Spectroscopy Laboratories of the University of Vienna in Germany with Volker Decker and Jürgen Popp. Fortunately, I too was lucky to be in the same university for some time in my PhD tenure. After completing his PhD, he worked as a National Postdoctoral Fellow, DST Serb NPDF, at the Macromolecular Laboratory of Professor Poonam Tandon in the Department of Physics, University of Lucknow. Then Dr. Ganguly moved to Prague in 2009 through the Institute of Organic Chemistry and Biochemistry IOCB postdoctoral program. Dr. Gangopadhyay has expertise in Raman, SERS, Raman optical activity, and other spectroscopic techniques. His primary research interests include Raman and SERS-based reaction, monitoring, and sensing of biomolecules and biological phenomena. He has several scientific publications in reputed journals such as Chemical Communications, Journal of Raman Spectroscopy, Spectrochemica Acta, Chemical Physics Letters, and so on. Rather than research, I am delighted to say he is a nice singer too. Raman Spectroscopy, so we know it's named after our Indian physicist Sir C.V. Raman, is a spectroscopic technique typically used to determine vibrational modes of molecules. On 28th February 1928. We know it is now we are celebrating it as National Science Day. Raman and his student Krishnan obtained a spectra of the modified scattering spectra separate from the incident light. We know Raman received the 1913 Nobel Prize in Physics for the discovery and was the first Asian to receive a Nobel Prize in any branch of science. Referring to the invention, Sir C.V. Raman later remarked, "When I got my Nobel Prize, I had spent hardly 200 rupees on my equipment, because that was the cost of that equipment that time." Okay, right. So with this remark, I may invite Dr. Gangopadhyay to deliver his talk on Raman spectroscopy and the detection of chirality. Okay, so welcome, Dr. Gangopadhyay.
Thank you. Thank you so much for such a kind and nice introduction. I'm very thankful to Dr. Shiju Abraham for inviting me in this webinar series. This is an interdisciplinary webinar series, which is a very good thing, and it's going for quite a few days. And today I will be delivering this talk, which concerns Raman spectroscopy and the detection of chirality. And both are very interesting topics. Raman spectroscopy in itself was a very remarkable discovery. And also chirality, or the handedness in molecules, this is also a very interesting topic. So I will discuss about how these two things can be combined and Raman spectroscopy can be used to study chirality. So without wasting time, I will move on to my presentation. I will share screen with you all. So can you see my screen?
Yes, that's right.
Okay. So as I have mentioned, the topic of today's my lecture will be Raman spectroscopy and the detection of chirality. This is a project on which I'm working right now here in the Institute of Organic Chemistry and Biochemistry in Prague. So this is where I work. This is the beautiful city of Prague in Czech Republic. This is the capital of Czech Republic. It is a medieval city. It's a very old city. And you can see the iconic Charles Bridge and the clock tower, and this is the old town square of Prague. So, and this is the institute where I work. This is the Institute of Organic Chemistry and Biochemistry. This is sponsored by the Czech Academy of Sciences. And this institute is divided into three different clusters: the chemical cluster, physical cluster, and biological cluster. So as I have done my PhD in physics, so I'm working as a part of the physics cluster, and the group in which I work is biomolecular spectroscopy. Primarily, my focus is on Raman spectroscopy, as I have been working in this field for since my PhD days, and now I have switched into a specialized Raman spectroscopy, that is Raman optical activity. I will get into the details of that later. But first of all, we should know what is Raman spectroscopy. Raman spectroscopy, if we have some idea, some of you have some idea about it, you know that Raman spectroscopy belongs to the group of vibrational spectroscopies. So what is a vibrational spectroscopy? In vibrational spectroscopy, we observe different vibrations within a molecule. So vibrational spectroscopy gives us an idea about the different chemical bonds that are present in a molecule and the different vibrations that are taking place. And from that, we can get an idea about the structure and the chemical composition of different molecules. Raman spectroscopy is based on the Raman effect. As Dr. Abraham has mentioned, the Raman effect was discovered by Sir C.V. Raman, for which he got the Nobel Prize. This was his instrument in which he worked, and he discovered the Raman effect. Another important aspect of Raman spectroscopy is that a Raman spectrum serves as a fingerprint for any sample. It's different for all molecules, like our fingerprint is different for all human beings. The Raman spectrum will be different for all molecules, and it reflects the idea about the different chemical bonds that are present in the material. And also the Raman spectroscopy can give us an idea about a chemical composition of any mixture, and we can detect precise amounts of a sample. This is Sir C.V. Raman. He was born in 7th November 1888 in Trichurapalli. This is the house in which he lived in his childhood. his parents are Chandrasekhar Iyer and Parvati Ammal. And after completing his schooling and his initial studies from Chennai, he moved to Kolkata to work. And during his work, he worked as a researcher. And later he got a professorship in IACS, the Indian Association of Cultivation of Sciences in Kolkata, where he did most of his research work. This is the first Raman spectrograph through which he recorded the Raman spectrum in 28th February 1928. He observed very interesting, his observation was very interesting because here you can see, this is the incident light from mercury arc lamp, which passes through a blue filter. So there are these bands of a specific color. When he observed the sunlight, he used a telescopic lens focusing system to focus sunlight into the sample. And after that, he found that there are many extra lines which passes after passing through liquid benzene. So something is happening, some extra lines are appearing in mercury arc lamp spectrum when it passes through liquid benzene. This was the first observation of Raman, from which he could explain the presence of these extra lines of different color or different wavelength. So from this idea, he predicted that there is not just elastic scattering, or which was known as Rayleigh scattering. Raman was working on this concept of scattering for a very long time. And we all know that the Rayleigh scattering, it's inversely proportional to the fourth power of wavelength. So the lower wavelength photons are scattered more. And this was the principle that Rayleigh described, and he described why the sky appears blue, because the lower wavelength is scattered more. And due to this scattering, the sky appears blue. So Raman was working on this concept, but he found that this Rayleigh scattering is a result of elastic scattering, but there can be some inelastic scattering which may give rise to some extra bands. And when he studied deeper into this, he found out the Raman effect, and he published his new radiation, the new type of secondary radiation resulting as a result of inelastic scattering. This was his publication. It was a very small report published in Nature. And this publication was a remarkable discovery considering the times, and he got the Nobel Prize for this. And this was the paper, A New Radiation, which was published in Indian Journal of Physics. So this was the initiation of the Raman effect. So how does this occur? Well, we know that light and matter can interact in different possible ways. One thing can be that some part of light may be absorbed in matter, some may be transmitted, or some may be reflected. There is another process called absorption and emission, which is fluorescence emission. So this is another topic which I will not go deeper into. Another process is scattering. Light can be scattered by when it interacts with matter. So Raman effect is a scattering effect, as I have mentioned. In Rayleigh, what happens is that when there is an incident radiation, it may, with energy h nu naught, it may be excited to a virtual state, because this is a highly intense energy. It will be excited to a virtual state, and then it will come back to the ground state and emit the same energy, scatter the same energy of the radiation with the same frequency. So in Rayleigh, we see that the incident frequency and the scattered frequency is same. But what Raman observed is that there can be a difference in frequency, which may result in a vibrational, due to a vibrational involvement in it. This vibrational energy is h nu 1, which is the difference between two vibrational states. That is the lowest vibrational ground state and the excited vibrational state. So in this way, he predicted that there can be a difference, either a red shift or a blue shift in the incident photons. And these red shifted ones are called Stokes scattered photons, and the blue shifted ones are called anti-Stokes. But Stokes didn't have any role in the Raman effect. This was just named in resemblance with the fluorescence Stokes shifts. But Stokes didn't have any role to play in Raman effect. Well, so the Raman effect was discovered in 1928, and he got the Nobel Prize in 1930. But after that, the application was very difficult. The application was difficult in a sense that when it is not a very easy process to focus sunlight through a telescopic lens setup and study samples. That is a very cumbersome process which Raman used, but it's not practically not applicable. So we need a very high intense source for recording Raman spectra, which was not available at that moment. It was almost after 30 years, more than 30 years, that laser was discovered. And the first laser was built by Mayman in 1960, which he devised based on the theoretical work done by Towns and Schallow, which was published in 1958. This basically, the laser was developed based on Einstein's idea of wave-particle duality, which was also proposed about the same time as Raman's discovery, more than 30 years earlier. But these ideas were combined, and then the laser was built in 1960. Initially, it was called MESR, or microwave amplification by stimulated emission of radiation. But when laser was discovered, it was found that laser has three interesting properties. One, it is monochromatic, that is, it has only single frequency or single wavelength in it. It is directional. If you have seen a laser torch, you know that it's very directional. It doesn't, it is not moving in different directions. It is moving in one particular direction. Another thing is that it's coherent. So these three properties of laser light make it a very useful and highly intense source of light. But at the same time, it is much more hazardous than ordinary light. That means it can cause harm if someone is exposed to laser directly on the skin or on the eyes. It may be harmful. And laser light can deposit a lot of energy within a small area. This is a very important aspect of laser light, which was explored by spectroscopists, and the Raman spectroscopy got a major boost when laser was invented. So I will show you a small video how laser works. Laser basically works when population inversion takes place. That is, an atom moves to its excited state by spontaneous absorption. At that moment, any photon can stimulate emission from it. So if a photon with frequency nu is incident on that atom, it will move from excited state to ground state, and it will emit another photon having the same frequency. And that photon in turn can stimulate other atoms to come from excited to ground state. This process is called stimulated emission, and this stimulated emission multiplies the photons. The photons are multiplied continuously within the laser tube, and which is called a photomultiplier tube. And what we get is a resulting avalanche of photons, which are coherent, which are monochromatic and unidirectional. So this is how a laser works. So after the discovery of laser, we have developed many modern Raman spectrometers, which have microscopes, and the lasers are used, and there's this focusing optics, and we use a grating for separating the wavelengths or dispersing the wavelengths. And we observe the intensity at each particular wavelength, which is plotted as a Raman spectrum. The Raman spectrum is basically Raman intensity versus wave number, that is the inverse of wavelength. And thus we see mostly we observe Stokes lines in the Raman spectrum, but there are some instruments which can record anti-Stokes also. But what we commonly use is Stokes-Raman spectrum. So after the discovery of Raman spectroscopy, the Raman spectrometer can be used for two purposes. The first purpose is for recording Raman spectra, which look like this. And the second purpose is for Raman imaging. In Raman spectroscopy, or when we observe the Raman spectra, we can get discrete information at distinct positions or at points within a sample. In Raman imaging, we can combine the Raman spectra of different points, and based on the differences in the Raman spectra, we can assign different colors, and we can get an image of the sample, of a particular area within the sample. So when I started my PhD in Banaras Hindu University in Varanasi, there I was working in the Raman spectroscopy lab of Professor Ranjan Kumar Singh. And in that lab, I have used two different Raman spectrometers, which are from the same company. It's a Renishaw by Renishaw. So this was a modern Raman microscope, which was capable of recording, doing Raman imaging. And this was an old Raman spectrometer in which we could record Raman spectra only. Then when I was working in Jena in Germany, I was working on this Raman spectrometer, which is a Raman RxN1 microprobe by Kaiser. This was a very sensitive Raman spectrometer, and it was equipped with 785 nanometer laser. Right now in IOCB Prague, I'm working on Raman optical activity spectrometer. Raman optical activity spectrometer is a specialized Raman spectrometer in which we can measure Raman optical activity. That is the difference between right-handed and left-handed polarized light intensities, which I will discuss later. So I'm working on this spectrometer right now. It is capable of recording both Raman and Raman optical active spectra. Now here you can see how a Raman spectrum looks. So Raman spectrum, basically, as I've mentioned, Raman spectrum is a reflection of the vibrations within a molecule. So there can be different kind of vibrations. So as I've mentioned, Raman spectra is plotted in Raman intensity versus the wave number. So in the wave number range of 2500 to 3500, what we observe is mostly the stretching vibrations of hydrogen, like the CH stretching, NH stretching, OH stretching. These vibrations lie in this wave number range. In the range between 2000 and 2500, we observe triple bond stretching vibrations, like the C triple bond N, C triple bond C stretching vibrations. In the wave number range 1500 to 2000, we observe double bond stretching, like CN stretching, CO stretching, CC stretching. And below that, below 1500 centimeter inverse is the fingerprint region, which has contribution from a number of bending and deformation vibrations like scissoring, twisting, rocking, wagging. You can see the animation of the different vibrations. So this has a combination of a number of vibrations, and this is called fingerprint region because this will be different for different molecules. This will never be the same for two different molecules. So by any expert who has expertise in studying Raman spectra can study these bands and assign different vibrations corresponding to different Raman bands. And we can get a clear idea about the composition of the sample, about the different molecular bonds, different bonds that are present within the sample. And even we can detect very tiny concentrations of samples based on some Raman marker bands. So this is what I have been doing when I was in India. So I was like sensing very small amount of samples, and I was monitoring chemical reactions, etc. So what are the advantages of Raman spectroscopy? There are very few very important advantages. The first one is that it is very sensitive to small changes. Even a small change in the sample will be reflected in the Raman spectrum. It is a non-destructive, non-invasive. Raman spectroscopy doesn't destroy the sample. So you can do a Raman spectra for a sample and then you can use it for doing some other study. The third thing is that it requires limited sample preparation. In fact, we need very less sample for recording Raman spectra, and we can, it's possible to prepare the sample very easily, unlike some other processes like FTIR spectroscopy, where specific sample preparation is needed for recording the spectra. The analysis is very quick. You have the Raman spectra in front of you, and if you can assign the bands, the analysis is pretty easy. And it is suitable for aqueous solution, unlike IR, which is not suitable for aqueous solutions. Raman is very suitable for studying aqueous solutions. But there are some limitations of Raman spectroscopy. One is the detection limit. For very small concentrations, Raman spectroscopy fails because it is a very sensitive technique, and we have to use very high intensity of incident radiation, that is laser. Even then, we have very less scattered photons, Raman scattered photons, because 1 in a 10 million, 1 in a million photons will get Raman scattered, which is very hard to detect. We need very strong detectors for getting the Raman spectra. So the detection limit of Raman is very low. Another thing is that it is obscured by fluorescent signal. So if there is fluorescence in the sample, the fluorescence will overcome the Raman bands because the Raman bands are weak. And for dark samples also, it is very hard to record the Raman spectrum. Well, what is the use of Raman spectroscopy? So Raman spectroscopy is extensively used in several fields, which range from biological sciences, medical sciences, pharmaceutics, material science, agricultural science, geology, archaeology, forensic science, and many more. And some of the major uses are, I have already mentioned, but I will list them once again. Identifying or detecting some specific compounds, in characterizing some newly synthesized compound. It can be used in studying the interaction of molecules. It can be used in observing some minor structural changes taking place in a molecule. And it can be used in monitoring chemical reactions, that we can observe structural changes that are taking place during a chemical reaction, which is a very important use of Raman spectroscopy. Now we'll come to the second interesting part of my topic, that is chirality. Well, we all know, as we all have studied science, we have this idea about chirality, that chirality is called handedness. If we see our left hand and right hand, these cannot be superimposed. So this is the concept of chirality. If there are two species, which is the mirror image, one is the mirror image of the other, and cannot be superimposed, then these objects are called chiral objects. But if they can be superimposed, they are achiral objects. So this is called chirality. This concept is called chirality. And this objects that have a handedness or a left-handed, right-handed manner are called chiral. And those that do not have this kind of handedness are called achiral. As you can see, our feet and shoes are chiral, but the socks are achiral. Well, the next thing is optical activity or birefringence. This is a property of a sample that can rotate plane polarized light. Suppose we have a plane polarized light, and a sample has the property of rotating this plane of polarization towards left, then it's called a levorotatory. And if another sample has can rotate this plane of polarization towards right, it's called dextrorotatory. So usually such samples exist in the D and L, or the dextro and levo forms, and these two forms are called enantiomers. So there are plenty of samples in nature, plenty of molecules in nature which exhibit this optical activity property, and they exist in two enantiomeric forms, dextro and levorotatory forms. The next thing is circular dichroism. Circular dichroism, it's similar to birefringence, but it's for circularly polarized light. If we have right-handed and left-handed circularly polarized light, and if the sample absorbs this right-handed and left-handed circularly polarized light differently, that there's a difference between intensity. So this process is called circular dichroism, and based on circular dichroism, this spectroscopic field has developed, the CD spectroscopy, or the electronic circular dichroism spectroscopy. This can differentiate the D and L enantiomers of which exhibit this circular dichroism property. And this was further developed into vibrational optical activity, or VOA, which has two parts. One is vibrational circular dichroism, where there's a difference in intensity of right-handed and left-handed circularly polarized light when they absorb the IR during the IR spectroscopy, and we get a difference in spectrum. And the another one is Raman optical activity. In Raman optical activity, what happens is that the Raman scattered light by left and right circularly polarized light has different intensity. And this difference in intensity, or IR minus IL, when it's plotted, it shows us some positive and some negative peaks. The positive peaks show us that the IR is stronger than IL for those particular vibrations, and the negative peak shows that the IL is stronger than IR. So, but the important thing which we observe in Raman optical activity is that when we take a dextro and levo, or the two enantiomers of the sample, we get mirror image spectra. So this is the very interesting thing about Raman optical activity, that for two enantiomers, we get exactly mirror image in the spectra. The Raman spectrum is the same for both forms, but the ROA spectrum is the mirror image. So this gives us information about chiral centers, and about the right-handedness and the left-handedness of different bonds present within the molecule. Now, classical Raman spectroscopy has some limitations. The main limitations of classical Raman spectroscopy are that it's not capable of studying molecules that have low Raman efficiency, and it's not very suitable when the sample concentration is very low. So to overcome these two main limitations of Raman spectroscopy, there are different techniques that are developed to enhance the Raman signal. So the Raman signal can be enhanced by using different techniques like surface enhanced Raman scattering, surface enhanced resonance Raman scattering, tip enhanced Raman scattering, and many other techniques, out of which I will be talking about the surface enhanced Raman scattering now. Surface enhanced Raman scattering is that when you have such a sample which doesn't give you very good Raman spectra, even when the concentration is quite high. It gives very poor signal to noise ratio. But the same sample at a very low concentration can produce excellent signal in surface enhanced Raman scattering. But how is it obtained? It's obtained when this sample, or which we call our ANALYTE in case of SERS, the ANALYTE is adsorbed on a metal surface. The metal surface can be silver surface, gold surface, or other nanomaterial surface. So mostly commonly used are silver and gold substrates. So when this ANALYTE is adsorbed on a silver or gold surface, there can be two effects. One is the electromagnetic effect, and another is the chemical effect. Now, Raman spectrum, or the intensity of Raman spectra, is governed by this formula, where alpha is the polarizability and E is the electric field. So in case of electromagnetic effect, due to the plasmon oscillations in the vicinity of the metal surface, there can be an enhancement in the electric field, the localized electromagnetic field. And this localized electromagnetic field may further influence the enhancement of the Raman signal coming from that ANALYTE. Another process is the chemical effect. In chemical effect, what happens is that there can be direct attachment of the ANALYTE with the metal surface, and by charge transfer, this polarizability value may increase, and this may cause a huge enhancement in the Raman signal. So this is how we record. Most commonly used, there are two kinds of SERS substrates that we use, are the colloidal nanoparticles of gold or silver, and other is the silver island film, or thin films, where we deposit a thin layer of silver or gold on a glass substrate. This is how we record the SERS spectra. We have our substrate, and we put a drop of the ANALYTE solution, and then we can directly put it under the Raman microscope, and we record the Raman scattered signal through a detector, and we get SERS spectra in this way. So what are the advantages and disadvantages of SERS? In SERS, the first advantage is that we can record for very low sample concentrations. Even picomolar or femtomolar concentrations can be recorded using SERS. Another advantage is that fluorescence quenching. If the sample is fluorescent, it will not affect the SERS spectrum. We may get very strong SERS signal from such samples. The third advantage will be surface selectivity and orientation. We can select a surface, and then we can control the enhancement. There are some particular groups like the thiol group, which is more which can absorb easily on the metal surface and thus produce stronger SERS signal. And the disadvantages of SERS are that there are some SERS active and inactive molecules. Not all molecules will produce SERS spectra. Reproducibility is a big question in SERS spectra. You may not get exactly the same SERS spectra every time you record it because of the interaction of ANALYTE with the substrate. So the ANALYTE may interact differently at different instances with the substrate, and thus you may not get the same spectra every time you record it. So in order to improve the reproducibility, we try to improve the quality of the SERS substrate that we produce. And mostly we have seen that the thin film substrates produce better reproducible spectra than the colloidal substrates. Well, that is a different aspect, which I shouldn't discuss now. It will become too long. So I will come to the topic the main topic of my lecture today, which is the surface enhanced Raman optical activity, combining two spectroscopies into one. I have discussed about two spectroscopies. One is the surface enhanced Raman spectroscopy, which is a very advanced Raman spectroscopic technique, which can produce huge enhancement of Raman signal. Another one is the Raman optical activity, or where we observe the enantiomers, the dextro and levo enantiomers of a molecule. So, but can these two spectroscopies be combined, or can we record surface enhanced Raman optical activity? Combination of these two spectroscopies, this has been a dream of physical chemists and spectroscopists for a very long time. But the problem is that Raman optical activity spectroscopy gives very weak signal, and we get a very low ROA by Raman intensity ratio, which is called circular intensity difference, or CID. If this ratio lies in a range of at least 10 power minus 4, then we may say that we have sufficient Raman optical activity signal. But you can imagine Raman itself is a very weak technique. It gives very poor signal, and Raman optical activity is even weaker by a factor of 10 power minus 4. So it's extremely weak. And is it possible to enhance it by surface enhanced Raman optical activity? Theoretical analysis done about 10 to 15 years ago, they found that SEROA is possible. So they have some reports where they have said that SEROA is possible, but there were some experimental attempts, but all the experimental attempts were inconclusive. I have shown some of the experimental attempts here. This was published in 2011 in ChemCom, and you can see that these spectra don't look very convincing. Even for the enantiomers, they don't look exactly like mirror images. So it's a big question. There are some other works that were published in 2012. They have published, you can see the surface enhanced Raman optical activity intensity is just 30, while the SERS is in 10 power 6. So the CID ratio comes out to be 10 power minus 6, which is very low. And also for this, in this paper, which was published in Nature Chemistry, they have shown that for the two enantiomers, D-tryptophan and L-tryptophan, but the spectra don't look like mirror images, and their CID ratio is very low. And also they have reported that they could not reproduce their spectra. So these are two big questions. Why are these surface enhanced Raman optical activity spectra that they have recorded? These are not mirror image. So, and these are not reproducible. So are these really spectra, or are these some artifacts? But the authors themselves were confused. But these were the first attempts to record surface enhanced Raman optical activity, but the experimental results were not at all very convincing. So with this idea, we started this work here in IUCB Prague, and our main motto was to achieve reproducible surface enhanced Raman optical activity. And I have tried to utilize my expertise in surface enhanced Raman spectroscopy, and by using this concept. This concept was a very unique concept which was proposed in Science in 2007, and there were some people who followed up this concept, that can achiral molecules become chiral when adsorbed at surfaces? So can a metal surface of gold or silver induce some chirality in achiral molecules? In principle, this can be possible, but how? Because when a chiral molecule is adsorbed on a metal surface, the metal surface can induce two things in it. One is that it reduces the symmetry of the adsorbate complex, or the analyte metal adsorbate complex. The second thing is that there can be surface interactions, or the distortion in molecular frame. So these two things can somehow distort the achiral molecule when it's on the metal surface, and they have observed that there is some distortion in the achiral molecule when it's on the metal surface, and it may have some induced chirality. But this induction of chirality may be only local. Local, I mean that it may give rise to some L isomers and some D isomers, and globally the entire mixture may remain achiral. So we may have equal number of L and D isomers. So it will be impossible to detect in surface enhanced Raman optical activity. However, homochirality can be achieved using a chiral modifier, which I will show. A chiral modifier can induce homochirality in a racemic mixture, or in an achiral solution which has equal number of right and left-handed isomers. So if we have a racemic mixture which has equal number of right and left-handed isomers, and we put a very small amount of a chiral modifier or a chiral molecule in it, suppose 5 mole% of a chiral modifier in it. So the right-handed chiral modifier will align all the molecules present within the racemic mixture towards the right-handed orientation, and the left-handed modifier will align all the molecules, all the left as well as right-handed molecules in the racemic mixture in the left-handed orientation, and we may get surface-enhanced Raman optical activity spectrum. So this was the concept of surgeons and soldiers, where this chiral modifier in very small amount serves as a surgeon, and these soldiers are ordered to be aligned in left or right-handed orientation by this surgeon, and they follow the surgeon's instructions, and they are ordered in a particular orientation. So using this concept, we have tried to transfer chirality from a chiral modifier or surgeon to an achiral linker or a soldier. So we have used different achiral linker molecules, which are 2-mercaptopyridine, 4-mercaptophenol, 2-mercaptopyrimidine, 4-mercaptopyridine. These achiral molecules we have used as linkers. Now, why we have selected these achiral molecules particularly? Because these achiral molecules are known to have very strong surface enhancement properties. All these have the thiol group, and they can produce excellent enhancement in surface enhanced Raman spectra. So we have tried to modify these achiral molecules and induce chirality in them by using a chiral modifier. So we have primarily used 3 chiral modifiers: L and D tartaric acid, L and D alanine, and L and D arginine. So these we have used as chiral modifiers, and you can see this chiral modifier can align it to the dextro or the levo form. And what we observe is not the surface enhanced Raman spectrum from the chiral molecule, but it's from the achiral linker. So this is but for the different chiral modifier, the D and the L chiral modifier, we get mirror image spectra. And the CID ratio is very high. It's in the range of 10⁻⁻3, which is considerably high when we consider surface enhanced Raman optical activity. So these are reproducible surface enhanced Raman optical activity spectra, and we observe the surface enhanced Raman optical activity from achiral molecule, which is also a remarkable thing. We observe Raman optical activity from achiral molecules due to surface induced chirality, which is induced by a chiral modifier. So how we did it? First of all, we prepared the silver nanoparticles in colloidal form, which were used for this study. This is the absorption spectrum of the colloid only. When we used 2-mercaptopyridine, or the linker molecule, for which we will observe the source, it broadened. There was a broadening in the absorption spectra, and we have used L-tartaric acid in very small amount, about 5 mole%, and it doesn't change the absorption pattern. So we have used HCl for aggregation of the colloids so that we get better source enhancement. After that, it looks such a broadened absorption peak. And as we have used 532 nanometer laser, you see that it's absorbing in this 532 nanometer range. So there is a possibility of resonance when we observe the surface enhanced Raman spectra. And this resonance may give us very strong bands in SERS as well as in Raman optical, surface enhanced Raman optical activity as well. And here I have shown you the electronic circular dichroism spectra. You see there is nothing. It's almost zero signal in circular dichroism. That is, the solution as a whole, it's not chiral. Chirality is present only on the surface. On the surface, I mean where the analyte is attached to the gold surface. It's a surface phenomenon. That's why the solution as a whole is not chiral. But when we record the surface enhanced Raman optical activity spectra, we get mirror image spectrum for the 2 enantiomers. You see the Raman spectrum has intensity in 10⁸, and this has intensity in 10⁵. So the CID ratio is 10⁻⁻3, which is quite high. And we have also tested for the reproducibility of our results these set of spectra that I'm showing in the left side of my slide, these were recorded in my laboratory where I work in IOCB Prague. And we have reproduced this spectra in another instrument, which is in another city in Czech Republic, in Olomouc. They have a very sophisticated Raman optical activity instrument, and we have reproduced the same spectra in that laboratory. So we have checked the three most important aspects for recording surface enhanced Raman optical activity, which were not done before this ever. Experimentally, we have produced reproducible spectra, reproducible Raman optical activity spectra. We have seen that there's mirror image of the two enantiomers, the D and L form. And the third aspect that we have discovered is that the CID is also in the range of 10⁻⁻3, which is very much acceptable as surface enhanced Raman optical activity. So this was what we did. And as future prospects, so the work that I have discovered now is that we have shown experimentally reproducible surface enhanced Raman optical activity, or we have combined the two spectroscopic techniques, the surface enhanced Raman scattering and Raman optical activity into one, and we have successfully produced a reproducible spectra. But we have done this from ACHIRAL molecules. In fact, we are observing the spectra from ACHIRAL molecules by inducing some chirality in it. But so far, we were not able to observe the surface enhanced Raman optical activity of chiral molecules. But why is it difficult? Why is it difficult to obtain surface enhanced Raman optical activity from chiral molecules? The question is not very simple to answer. There can be several factors, because the chiral molecules have some intrinsic chirality. And when we use a surface like a gold or silver nanoparticles, there can be some induced chirality. And these two chiralities may interfere, which may not be very strong and may not be able to detect. And there can be many other factors which make it difficult to obtain surface enhanced Raman optical activity from chiral molecules. But we are trying, and this is our main motive, to record surface enhanced Raman optical activity. And in this concept, we are trying to build or synthesize some chiral colloids, or capping colloids with maybe some chiral molecules. And this chirality within the colloids may in future lead us to record the surface enhanced Raman optical activity from chiral molecules. Well, this was mostly what I wanted to say about Raman spectroscopy and surface enhanced Raman spectroscopy, and how these techniques can be used to detect chirality in molecules. So I am very thankful to you for listening and for your patience. I would like to acknowledge some people and some funding agencies. So my mentor, Professor Peter Bosch, in which group I'm working now, my collaborators, Jaroslav Shevestik and Josef Kapitan, and Momita Das, who is the main worker in this project. So I'd like to thank you all. And if you want to ask something, I would be very happy to answer your questions.
Okay. Okay, thank you, Dr. Gangopadhyay, for the nice, wonderful talk on Raman spectroscopy as well as surface enhanced Raman spectroscopy, as well as okay, these all things. We know science as well as research usually break the boundary between the countries. That's why we know even the founder of this Raman effect, Sir C.V. Raman, is from India. But we know now a lot of research going on many countries abroad, many countries like in Germany as well as in Czech Republic. A lot of things are going on in Raman spectroscopy. So we got a broad as well as sometimes some areas of focused depth knowledge on Raman spectroscopy. Now it is time for open discussion. If any of the participants or students or faculty want to ask something, you can ask directly here, or they can put the question in the chat box. Also on the chat box, there will be one feedback form. Please don't forget to fill that form. Okay, it is now open for discussion.
Hello.
Hello. Yes.
Hello. Hello, Dr. Gangopadhyay. Good afternoon.
Good afternoon.
I'm Dr. Sinosh. a faculty of microbiology, the same
Okay.
institution. Okay. First of all, thank you very much for your excellent talk. You have highlighted the role of surface enhanced Raman spectroscopy, especially by transferring of the chirality from chiral modifier to a chiral linker. That concept is really fantastic, and you have mentioned very clearly the aspects of this surface enhanced Raman spectroscopy in variety of scientific field. And being a biology person, you know that we structural biologists generally we used to use this kind of technologies, this kind of approaches for structural study of biomolecule. And I don't know really, I can ask this question, but this is just for a curiosity. I am asking: is it possible to use this surface enhanced Raman spectroscopy technique to identify or study uh, the uh, the structural aspects of a membrane protein? Because any other structure, if you look, membrane proteins are highly hydrophobic in nature. Even X-ray crystallography or circular dichorism or NMR, it is very, very difficult to study using this particular membrane protein. Is it possible to use this CR to provide the structural aspects of this membrane protein in terms of their the amino acid derivative, especially that there are the amino acids have a variety of isomeric form, isomeric shift. What do you think about that particular thing? That is my first question. And next one is the so-called modifier to linker when you are converting. What property we are looking for the converter actually? What should be the ideal characteristic features of this converter? Could you please throw some light on that?
Okay, yes. Regarding your first question, that if you want to study the structural properties of membrane proteins, it's a very difficult task using surface enhanced Raman spectroscopy. And there are some reports where they have attempted to study proteins using surface enhanced Raman technique, but those are like still in the development stage. One aspect is that the proteins are not readily adsorbed on metal surfaces. So the adsorption of proteins of any biomolecule, if you want to do search from it, it has to be adsorbed on the metal surface. That's the primary requirement. So what you can do is you can functionalize your protein by substituting some amino acid, like by cysteine. Cysteine is the only amino acid which has a thiol group. So a thiol group is an excellent adsorber for SERS. So if you can functionalize your protein at some specific positions, maybe you can replace an amino acid by cysteine, which has a thiol group, then there's possibility that that protein may attach to our metal surface via that thiol group. And it's possible to record SERS spectra. So this is one thing. There are many other tricks that can be done to record surface enhanced Raman scattering from proteins. But as protein is a very long chain of amino acids, it's not possible to get structural information of all of it at once. It will be very complex. So you can do a zonal scanning, like substitute one position with cysteine and do a zonal structural scanning. And in this way, you can study the protein structure. This has been done, and this is also in the development stage, but this was successfully done by some people. Also in our group, some people are doing this kind of study.
So is it possible? Yeah, please carry on.
Okay. No, you can ask me.
Yeah, is it possible, the continuation of that one, is it possible to study the interaction, especially the protein-protein or protein DNA or any other molecular conjugate, the interaction studies?
Yes,
how better
it is possible to study any kind of molecular interaction using Raman as well as SERS technique. So initially, it's not necessary, if you have sufficient concentration of your protein, it's not necessary to go into surface enhanced Raman. If you can study it by Raman spectroscopy, that's good enough. And for that, you need not functionalize or do anything. You can, in Raman spectroscopy, you can study proteins very easily. There are many reports you will find that they have studied proteins using Raman spectroscopy, and also interaction of proteins. So there is one group of Dr. Samrat Mukhopadhyay in IISER Mohali who do this kind of work. So you can go through their works.
Okay.
So, okay, regarding the second question, how the modifier exactly interacts and produces. So I have shown in my slide about the surgeons and soldiers. So this is a very old thing. This concept was presented many years back. Surgeons and soldiers. And this is some property that the chiral modifier, when we put it into a racemic mixture, this induce a very small amount can induce this similar handedness or homochirality. This is a property. So I'm not sure how exactly this happens. There can be several possibilities. Here I have shown one, that it may get arranged as a helix, a right-handed helix and a left-handed helix. And there are some aspects where they just can be aligned in some other form. But this is a property that a chiral molecule can induce homochirality in a racemic mixture. It's not only applicable for achiral molecules. It can also induce homochirality in chiral molecules. Suppose we have many chiral molecules, almost equal number of left-handed and right-handed isomers. Then a small amount of another chiral molecule can induce this homochirality. All of it will be arranged in a similar alignment, left-handed, either left-handed or right-handed, based on the handedness of this modifier.
Thank you, Dr. Gangopadhyay. Thank you. Thanks a lot.
Okay, welcome.
Okay, any more questions from students?
Right now, what is the cost of Raman Spectrometer?
Yeah,
sorry.
You want to know the price?
You want to know the price of a Raman spectrometer?
Yeah.
I think in Indian rupees it will cost around. It's very expensive. It will be at least 70 to 80 lakhs Indian rupees, just for spectrometer. If you want to do Raman imaging and all sophisticated stuff, it will be more than 1 crore.
Okay. Some questions are in the chat box from the students, I think. So
I don't know. I can't access.
I will read here. So they become more asked. So does Raman spectroscopy have any use in pharmaceutical industry?
Yes, of course. Raman spectroscopy has several applications in pharmaceutical industry. First thing is we study the applicability of a drug, or for different polymorphic forms of a drug. We can study how a drug metabolizes into its metabolite before it functions in the body. Mostly all drugs change its form when it's in the body, and then it functions in the body. So we can study that metabolic process, or how it changes, and we can study the effectivity of drug delivery. Raman spectroscopy is also capable of determining the proper dosage of a drug. So there are several applications of Raman spectroscopy in pharmaceutical industry. Also, we can study some, we call it like co-crystalline drugs. Such things can be studied, and it leads to advanced pharmaceutical design. So there are many applications of Raman spectroscopy in pharmaceutical industry.
Okay, good. So there is also one more question from Ashwin S. Sir, can you please explain how to prepare sample for Raman spectrum? So how we are just preparing the sample for this Raman spectrum? It's just maybe the procedure. Yeah, maybe for curiosity. Yeah.
Okay. As I have shown you this Raman spectrometer, it's a very this is the basic structure of a Raman spectrometer. If you can see, you just need to place your sample below the microscope in this kind of Raman spectrometer. And in this, if there are some other where the laser is coming horizontally, you have to place your sample vertically. Mostly that's done for liquid samples. So here you can study solid samples. You just need a glass slide. You put your sample, and it should be flat, and you put it under the microscope, and that's it. Laser will fall on the sample. The sample will scatter radiation, and that scattered radiation will be detected by the detector. That's it. It's so simple, the sample preparation. Okay. In case of sample, the laser will come horizontally. You will put your liquid in a tube, and the that will scatter radiation and it will be detected. So it's pretty simple.
Sir,
Yes.
what is the main difference between surface enhanced Raman scattering and tip enhanced Raman scattering?
Okay, so both are enhancement techniques. In the case of surface enhanced, what we use is, I have shown you, these are two kinds of source substrates. One is the colloidal nanoparticles and one is the silver island film. So it's a film. On this film, we put sample and then we put it under the Raman microscope and we observe the spectrum. This is one technique, or we can observe it in colloidal nanoparticles. But tip enhanced is a different, there's some difference from surface enhanced. It is another technique where we used a nano tip, or I don't have a picture to show you right now, but it's a tip which has a few atoms of silver at the tip, or gold, whatever substrate you want to use, and it like this, the tip comes in contact with the sample, and actually it's like combination of Raman spectrometer with atomic force microscope. So these two things are combined, and the AFM tip falls on the sample, and then the AFM scans the sample, and the laser that it's put on the interface between the tip and the sample, and from there we record the spectra. So both are similar techniques, but just the substrate that's used for analyzing the sample is different.
Okay.
Obviously, tip enhanced Raman scattering is even much more sensitive than surface enhanced Raman scattering.
Okay. If more questions or fine. Okay. So dear participants, don't forget to fill the feedback form in the chat box. Proceed. There is no further question. Now I invite Adano to proceed further.
Now I invite Dr. Monisha, faculty of Department of Physics, for the vote of thanks.
Respected Principal, Sir, Honorable Resource Person, Dr. Debraj Gangopadhyay, Head of the Department, Dr. Rajapuram Sir, other faculty members, and dear students. It's a great honor and privilege to express a few words of gratitude on this occasion. First of all, I thank our principal, Sri Biju Sir, for giving us an opportunity to conduct this program in this international webinar series, ILLUMINISMO 2021. Thank you, sir, for your valuable suggestions and guidance. Now, I would like to extend my gratitude to our resource person, Dr. Debraj, for giving such an informative
I think Monisha is not there.
So,
Yeah,
okay, let me continue. So I would like to extend my gratitude to our resource person, Dr. Debraj, for such a wonderful talk on Raman Spectrometer and the detection of chirality. And we are very fortunate to have Dr. Debraj for today's session, who is an expert in many spectroscopic techniques, especially Raman spectroscopy. He has explained the Raman effect and its applications, like laser and about Raman spectrometer, about the property chirality, etc., in a very effective way. Thank you, sir, for spending your valuable time with us. Next, I thank our HOD, Dr. Ajit Kumar sir, Parvati Miss, and Dr. Shiju Abraham, who is the coordinator of this program, for their and I extend deep gratitude to all the faculties and students who are present here. Finally, I thank the organizing committee of ILLUMINISMO 2021 for their support. Once again, thank you all. Thank you.
Okay.